Hello everyone, this is Abzalur Rahman. In our today's class, we are going to discuss about the physical properties of haloalkanes and haloarenes. In our previous classes, we have discussed about the methods of preparation of haloalkanes and haloarenes, and after that we have discussed about the chemical properties of haloalkanes and then haloarenes. Now in our today's class, we will be discussing about the physical properties of both haloalkanes and haloarenes. Okay. So in these physical properties, first of all we will discuss about the solubility. First of all, solubility. Okay. So these haloalkanes and haloarenes, they are polar molecules. They are polar molecules. Okay. Now why they are polar? How we can say that a molecule is polar or non-polar? Okay, na? With the help of dipole moment, we can say that whether a molecule is polar or non-polar. Okay, na? If there is any charge separation, then this molecule will be called as polar molecule. Okay, and in both these haloalkanes and haloarenes, there is some charge separation. Means there will be some net dipole moment. Okay, now what is dipole moment? We know this dipole moment means it is the product of magnitude of charge and the distance between the charge. Okay, suppose if you consider the example of CH3Cl. Here the Cl will be del minus, consequently carbon will be del plus. Okay, so there is some charge separation. Okay, so if there is some charge separation in a molecule, okay, na, such type of molecule is called polar molecule. Okay, so these haloalkanes and haloarenes, they are polar molecules. But these haloalkanes and haloarenes, they are insoluble in water. Okay. Now question comes, why they are insoluble in water? Because the magnitude of intermolecular force of attraction that exists in these haloalkanes and haloarenes does not match with the magnitude of intermolecular force of attraction in water molecules. Okay, na? That's why they are insoluble in water. Okay, na? If their magnitude matches, na, so they can break the bonds that are present in water molecules. But because of the lower magnitude of intermolecular force of attraction in these haloalkanes and haloarenes, they cannot break the bonds that are present in water molecules. That's why they are insoluble in water. Okay. So both these haloalkanes and haloarenes, this haloalkane and haloarene, they are insoluble in water. Insoluble in water. Okay, insoluble in water. Okay. But these haloalkanes and haloarenes, they are soluble in some solvents having low polarity. Okay, for example petroleum ether or benzene or ether, chloroform, that is CHCl3, or carbon tetrachloride, etc. Okay, so they are insoluble in water molecules. Okay, but they are soluble in some solvents with low polarity. Okay, but it has been found that these haloalkanes and haloarenes, they are soluble in this low polarity solvent, but they are insoluble in water. Okay, so this is all about solubility. Okay, so next we are going to discuss about melting point and boiling point. Okay, so number 2 is melting point and boiling point. Suppose if we consider one hydrocarbon, CH4 methane molecule, and if we take its corresponding haloalkane, so this is methane, and its corresponding haloalkane, suppose CH3F, this is methyl fluoride or fluoromethane, or next one is chloromethane, bromomethane, and last one is iodomethane. Okay, na? So this is one alkane, but these are the corresponding haloalkane. Okay, fluoromethane, chloromethane, bromomethane, and iodomethane. Okay, now if we proceed from left to right, the boiling point of this molecule increases. Okay, now their boiling point. So here we have boiling point in Kelvin, their boiling point will continuously increase. Now why their boiling point increases? Because from left to right the molecular mass is increasing. Molecular mass, molecular size is increasing. Now if the molecular mass or molecular mass size increases, then van der Waals force of attraction will increase. Okay na? And if the van der Waals force of attraction increases, then the boiling point will consequently increase. Okay. So the boiling point is, this one is 111 Kelvin. This is 195 Kelvin. Okay. This is 249. This is 277. And this one is 315.5 Kelvin. 315.5 Kelvin. Okay. So here you see this boiling point is increasing continuously. Okay. And here you see this is hydrocarbon. This is one hydrocarbon, but this is one haloalkane. Here the intermolecular force of attraction increases. Okay na? In this haloalkane type compound, the intermolecular force of attraction is stronger than that of hydrocarbon. Is corresponding hydrocarbon, and the molecular mass is also increasing, and that's why the van der Waals force increases. So the boiling point also increases. Okay. So this is suppose number A. Number B. Now if we fix this alkyl group, okay na? If we fix this halogen group, if we fix this halogen group, suppose chlorine, okay, and if we increase the side chain, suppose this one is CH3Cl, chloromethane. If we increase the side chain, suppose this is CH3 CH2Cl, chloroethane, CH3 bond CH2 bond Cl. This is chloropropane, and this is chlorobutane, CH3 bond CH2 bond CH2 bond CH2 bond Cl. Okay. Here you see the halogen atom is same. Okay, but the side chain is increasing. Okay na? In this case also the boiling point will increase. Because the side chain is increasing. Side chain increasing means the molecular mass will increase. And if the molecular mass increases, van der Waals force of attraction will increase. And if van der Waals force of attraction increases, the boiling point will also increase. Okay na? So then melting point is, this one is 249 Kelvin. Here these are haloalkane, and this is, here we have boiling point in Kelvin. This one is having boiling point 249 Kelvin. This one is 285.5 Kelvin. Okay, this one is 320 Kelvin, and this one is 351.5 Kelvin. Okay, so here you see continuously the boiling point is increasing. Okay. So with the increasing side chain also, the boiling point of this haloalkanes increases if the halogen atom is fixed. Okay. Now for isomeric haloalkanes, number C. For isomeric haloalkanes, okay, with the increase in branching, the boiling point decreases. Okay. For isomeric haloalkanes, suppose question C, point C. For isomeric haloalkanes, boiling point decreases with the increase in branching. With branching, decreases with branching. Okay now. So suppose if we consider one example, suppose CH3 bond CH2 bond CH2 bond CH2 bond Cl. Okay. So what is the name? The name of this molecule is N-butyl chloride. Okay. N-butyl chloride. So its another isomer will be, here you see its another isomer is CH3 bond CH bond CH3 bond CH2 bond Cl. This is N-butyl chloride, and this one is isobutyl chloride. Okay. Here you see both of these molecule will have same molecular mass, same molecular formula, and the isomer is suppose CH3 bond CH2 bond CH bond Cl bond CH3. Okay, so this is sec butyl chloride, sec butyl chloride, and last one is tert butyl chloride. For example, CH3 bond C bond CH3 bond CH3 bond Cl. So this is tert butyl chloride, tert butyl chloride. Here you see all of these molecules, they have the same molecular mass, same molecular formula. Okay, but the boiling point decreases. Here this is here the boiling point will decrease from left to right, because from left to right the branching decreases. Sorry, the branching increases. Okay, now from left to right the branching increases. Okay, now so the boiling point will decrease. With the increase in branching, the boiling point decreases. Now question comes, why this with the increase in branching the boiling point decreases? Because with the increase in branching the surface area decreases. Here you see this molecule will have large surface area, but with the increase in branching the surface area is decreasing. And this surface area is related to van der Waals force of attraction. If the size decreases, then the van der Waals force of attraction will decrease. And if the van der Waals force of attraction decreases, then the boiling point will consequently decrease. Okay, so from left to right the size decreases, van der Waals force of attraction decreases, and the boiling point will also decrease. Okay, from left to right size is, okay, now with the increase size is decreasing. Okay, now so here you see boiling point for this one we have, this is 351.5 Kelvin. Okay, this one is 342 Kelvin, this one is 341, and this one is 324 Kelvin. Okay, so here you see from left to right the boiling point decreases. Means with the increase in branching the boiling point decreases. The reason is that with the increase in branching the surface area decreases. If surface area decreases, then the van der Waals force of attraction will decrease, and if the van der Waals force of attraction decreases, the boiling point will also decrease. Okay, so this is the trend for this molecule. Okay, now fixing the alkyl group, if we increase the number of halogens, halogen atoms. Okay, now so number D is by fixing this alkyl group. Okay, suppose if we consider the example of this one, number D, suppose CH2 Cl2. Sorry, now we consider CH3Cl, then CH2 Cl2, then CHCl3, and CCl4. Here you see from left to right, okay, the number of halogen atoms are increasing. Okay, now so with the increase in number of halogen atoms, the boiling point will increase. Because from left to right the molecular mass is increasing. Okay, so what is the boiling point? Here you see for this one we have 249 Kelvin, then we have boiling point. This one is 249 Kelvin, this one is 313 Kelvin, this one is 334 Kelvin, and this one is 350 Kelvin. Okay, so you see from left to right the boiling point is continuously increasing. Okay, so now you see, now for this haloarenes also, okay, if we consider one arene, suppose we have benzene ring, and its corresponding haloarene will be fluorobenzene, then chlorobenzene, then bromobenzene, and last one is iodobenzene. Okay, so for this haloarene molecules also, with the increase in the atomic mass of this halogen atom, the boiling point also increases. The boiling point of haloarene also increases. Okay, So here you see with the increase in the size of this halogen atom, here the size also increases, size or molecular atomic mass also increases, okay na. So with the increase in size of these halogen atoms, okay na, the boiling point of these halogens also increases, okay. So here we have boiling point in Kelvin, boiling point in Kelvin, okay. So this one is having 353 Kelvin, 353. So this is 353 Kelvin, 353 Kelvin. This one is 359 Kelvin, okay. This is 405, 429, and this last one is 462 Kelvin, 462 Kelvin, okay. So here you see from left to right, with the increase in molecular mass, the boiling point increases for this haloarenes also, okay. Now if we consider one dihalo compound, if we consider one dihalo, suppose 1,2-dichlorobenzene, or ortho-dichlorobenzene, then meta-dichlorobenzene, and para-dichlorobenzene, okay. So all these molecules are their isomers, So for this isomeric dihaloarenes, their boiling point is somewhat similar, okay. They have somewhat similar values, but their melting point is different. Melting point is quite different, okay. So for these molecules, their boiling point, if we consider their boiling point, then this one is boiling point having 453 boiling point. Here we have 446, and here we have 448 Kelvin. And if we consider this the melting point, here melting point also for this molecule, the melting point is 256 Kelvin. This is 249 Kelvin, and this is one is 323 Kelvin, okay. So for the isomeric dihaloarenes, their boiling point is quite similar, okay na. But this melting point is different. Here you see for this one we have 256 Kelvin, 249, and this one is 323. There is huge difference. Why? There is the boiling point of this 1,4-dichlorobenzene is higher than both these isomers, because this molecule is a trans molecule, okay. This is a stable molecule, so it will fit into its crystallities more tightly. That's why its boiling point is high compared to this molecule, okay. So if you compare this ortho and para isomer, okay, these ortho and para isomers are quite stable than this compared to this meta isomer, okay. That's why its melting point is low, but this will have some higher melting point value. Okay, now we are going to discuss about density, okay. Number E, we are going to discuss about the density, okay. So these alkyl fluoride and alkyl chloride, these alkyl fluoride and these alkyl chloride molecules are lighter than H2O. They are than H2O, okay, lighter than H2O. But these bromides and iodides, they are heavier than water molecules. They are heavier than water, okay. And for these haloalkanes, okay, the density increases with the increase in molecular mass. The density increases with the increase in molecular mass, okay. Suppose if you consider Ri, okay, alkyl iodide, then it will have a higher density than alkyl bromide, RBr, then RCl, then RCl, okay. So these molecules will have higher density than this bromide, than this chloride, okay. Last we are left with dipole moment. Okay. We'll see the dipole moment, okay. So number F, we have dipole moment. Okay. So if we consider this halogen, suppose fluorine, chlorine, bromine, and iodine, okay. Iodine. So if we consider their corresponding compound, suppose we consider CH3F, CH3Cl, CH3Br, and then CH3I, okay, CH3I, okay. So here you see from left to right, the atomic size increases. The atomic size of this fluorine, then chlorine, the atomic size increases. Atomic size increases, or their electronegativity decreases. Electronegativity decreases. Okay. So if you consider this molecule fluoromethane, chloromethane, bromomethane, iodomethane, the dipole moment should decrease in the order, in this order. Okay. So why in this order? Because this fluorine will have higher electronegativity. Okay, means it will have higher charge separation. Okay, so this will be del minus the del plus, and higher the charge separation, the more will be the dipole moment. Okay, we know this dipole moment is the product of magnitude of charge, mu is equal to q into r, or mu is equal to q into d. Okay, q means magnitude of charge and r means distance between the charge. Okay, so here you see, since this fluorine is highly electronegative, okay, so its capacity to to pull this electron density is higher. That's why the dipole moment value should decrease in this order. This CH3CF, first of all we have CH3CF, then CH3Cl, then CH3Br, then CH3I. But it has been found that there is some exception. There is some exception. It has been found that this chloromethane, this CH3Cl chloromethane has higher dipole moment than CH3F. So here is some exception. Here is some exception. Now question comes, sir, why? Okay, so if we put the value, we'll have the value here. This will have 1.860 divide. Okay, here mu value, dipole moment value. Okay, and it will have 1.847 divide. This one is 1.830 divide, and last one is 1.636 divide. Okay, so here you see this dipole moment is decreasing in this way. Means if you consider this one, this CH3F should have higher dipole moment value than this CH3Cl, but it is found that exceptionally this CH3Cl has higher dipole moment. Now question comes, sir, why? Because we know this dipole moment means this magnitude of charge and the distance between the charge, and after the calculation of dipole moment, it has been found that in case of this CH3Cl, the magnitude of its charge and this bond length is found to be higher than that of this CH3F. Okay, though it is highly electronegative del minus, but due to the smaller size and high electronegativity, it is having quite smaller bond length. Okay, as a result, the product of this charge and bond length comes out to be somewhat lower than that of CH3Cl. That's why it has been found that experimentally it has been found that this CH3Cl has higher dipole moment value than this CH3F. Okay, and it will decrease in this order. Okay, so this is all about the dipole moment of this haloalkane. And in case of haloarenes, the dipole moment value decreases from fluorobenzene to chlorobenzene, the iodobenzene. Okay, so it will continuously decrease. Okay, so in our today's class, what we have discussed about the physical properties of haloalkanes and haloarenes. Okay, first of all, we have seen the solubility. We have seen that these haloalkanes and haloarene molecules, they are polar molecules and they are insoluble in water. After that, we have discussed about boiling point and melting point. Okay, we have seen that with the increase in molecular mass, the boiling point increases because the van der Waals force of attraction increases. Okay, and this melting point depends upon the symmetry. Okay, now if the molecule is stable, symmetric, okay, now it will be more stable, or so it will fit into the crystal lattice more tightly, so it will have a higher melting point. Okay, and after that, we have discussed about this density. Density will decrease, the more the molecular mass, it will have higher density. And last we have discussed dipole moment. So this dipole moment value decreases in this order. So for today's class, up to this, in our next class we are left with only one topic in this chapter, that is optical activity. So tomorrow we'll complete our this chapter, haloalkanes and haloarenes. Thank you everyone.